Hey kids, Mr. Murray here, back on Mr. Murray's Math Land. Today we're taking a look at implicit differentiation, and this is an intro video, so hopefully I'll have a couple other videos for more advanced topics with it, applications of it. But this is just to try to get used to the whole idea of it. Okay, so as a warm-up, we're going to take this equation below and differentiate it with respect to x. And as you'll notice, there's multiple variables in it, as some word problems may have coming up in the future. And so we're going to take the derivative of this, or differentiate it, with respect to x. So what that means is maybe you've been kind of taking this for granted when we've been taking derivatives, that our equations have always been, y equals something in terms of x, or f of x equals something in terms of x. And so everything was always in terms of x that we were taking the derivative of. But that's what's called an explicit function. And this is something that's defined implicitly, meaning it's not just y equals, y is not solved for. So doing this is actually, it's not bad, it's a piece of cake. At least the basics here. And the major idea to get across is with respect to x, that's what this denominator represents in this Leibniz notation for derivatives. So the big idea is whatever variable you're doing the derivative with respect to, that's what you want to be on the lookout for. And so, for example, this first part of the expression, the derivative of x to the fourth, if it's the same variable, then you just treat it normally like you always do. Oh, the derivative of x to the fourth is 4x cubed. However, when you move along, and now you're about to take the derivative of a different variable, other than the one you're doing it with respect to, in this case, y. So here's the thing. You take the derivative of it, using any power rules or other rules you've accumulated by this point. So derivative of 5y cubed would be 15y squared. However, you then have to multiply by dy dx. And you're really using the chain rule there because y could represent something else, and so you're kind of using the chain rule where, hey, I'm multiplying by the derivative of the inner expression, multiplying by dy dx. When I move along here to the next one, plus 8z, the derivative of 8z is 8. But then I have to multiply by dz dx, the derivative of z with respect to x. And you see, that's why you don't need it when you do an x expression, because if you were doing 4x cubed, you would then multiply by dx over dx, which is just 1. So that's why we've kind of been blowing past that, glossing over it maybe so far in our derivative unit. But now it starts to really become important. And so continuing on the other side of the equation, the derivative of 17, that's a constant, that's 0, and times dc dx doesn't matter, it's 0, so boom, it's gone. The derivative of negative 9x, that's negative 9. And again, that's x, so I don't need to multiply by any additional notation. But the derivative of t squared, that's a different variable other than x, so that's 2t, and then times dt dx, multiplied by the derivative of t with respect to x. And that's it for the warm-up there. Just that idea of watching out for variables matching or not matching that which you are differentiating with respect to. Okay, so now let's try a slightly different problem. This is more along the lines of the problems you'll need to do with this. Find dy dx, which is what we've been finding with a lot of our other problems for this equation. And you'll notice now there's only two variables in it, as there often will be, just x and y. So here we go, and I'm going to get a little lazy here. I'm just going to take the derivative of this whole thing rather than write it on each side of the equation, as you really should if you were being extra formal. But here we go. anything that's x is normal. So derivative of 3x to the fourth, 12x cubed. Derivative of 2y to the fifth, hey, that's not an x expression, so this is where we're going to use our implicit differentiation. So that would be 10y to the fourth and times dy dx equals, and on the other side, you're doing the derivative of cosine of this quantity. So, hey, chain rule, just be, very disciplined. What's the derivative of cosine of something? Negative sine of that something. And now multiplied by the derivative of that inner expression. The derivative of y squared plus 3 is 2y, and right there I just took the derivative of a y expression. So I need to do dy dx. That's the derivative of y squared, 2y dy dx. And the plus 3, of course, drops out because that's a constant. And then moving along, the derivative of negative 8, that's a constant, so that's 0. So there is our first step. We're not done, because when it says find dy dx, that means you want a final step that says dy dx equals. And so I need to isolate, I need to solve for dy dx. And so as you'll notice, some of your terms have dy dx. This is all one big term, so it's all being multiplied. So what we're going to do, just use a little algebra from here on out to isolate dy dx. So I'm going to bring everything that has dy dx to one side. So, and anything that doesn't have dy dx, I'm going to move it to the other side. So this 10y to the fourth dy dx, I'll keep this on the left, and I'm going to bring this whole big chunk here to the right side just by, basically adding it. So now I'll have plus sine y squared plus 3 times 2y dy dx. And probably, let's face it, maybe it's nicer to put that 2y out in front as a coefficient. Maybe it looks a little nicer to have 2y sine of y squared plus 3 and have the dy dx at the back. Doesn't really matter, it's all multiplied, equals. And don't forget about this. Now this did not have dy dx, so I'm moving it to the other side of the equation. So I'm going to subtract 12x cubed. We call this, in the math world, it's a very technical term, we call this having a dy dx party on the left side, meaning everything on the left side should have dy dx. And if you don't have it, you're not invited to the party, you go to the other side. And we do this so that we can now factor out dy dx. It's just a big variable, essentially, so you can treat it that way. I'll factor dy dx out, and I'll have 10y to the fourth plus 2y sine of y squared plus 3 equals negative 12x cubed. And now, since I was able to factor it out, I'll just divide by that big quantity to solve for dy dx. So dy dx will be the negative 12x cubed on the other side divided by this giant quantity, right? To just cancel it from this side, and I'm putting it over here. And so I'll now have 10y to the fourth plus 2y sine of y squared plus 3. And that is our derivative. And so you'll see that they can get pretty ugly looking, when your original equation has x's and y's all over the place, your derivatives are going to be that much more complicated. So anybody want to do the second derivative of this now and do yeah, well, they'll be coming up if you were thinking no. So I'll do one more example here, just so you can feel comfortable. If you want to hit pause and try to do the derivative on your own, feel free. But we're going to take the derivative of this with respect to x. And this whole thing I'm doing right here, where I'm writing this derivative of all of this with respect to x, it's not necessary. Some people will go right to the next step without writing any of this notation, but I kind of like to write it. And all right, so here we go. Our first thing we're coming to is the derivative of e to the 2y cubed. So, be good with your chain rule. The derivative of e to the something is e to that something, e to the 2y cubed. but then multiplied by the derivative of that exponent, the derivative of that something. And the derivative of 2y cubed is 6y squared dy dx. And now here we go, doing the derivative of negative x squared y, that's going to require the product rule. So as always, if you're good with your product rule, you can do it right in your head. Go for it. If you like to make a little chart, a little organization, whatever helps you get the job done. So a is negative x squared and b is y. So a prime is negative 2x and b prime is the derivative of y, and that is where you need implicit differentiation, because just at that step you're doing the derivative of something other than y, other than x. So now our inners plus outers are going to give me negative 2xy minus x squared dy dx. And again, maybe you don't need that whole little chart system to do that, and that's totally fine if you can go right to that. And the derivative on the other side, derivative of x, that's an x, so that's normal. That's just 1. Derivative of 7, that's a constant, that drops out. So here we go. We want to solve for dy dx. And so we're going to have a dy dx party. And, maybe this right here, I'll clean up a little bit. A lot of this algebra, the isolation part, can be done in your head if you're comfortable. This term I'm going to move to the other side. It doesn't have a dy dx, so I'm just going to add that to the other side. This term I'm going to leave here. It's got a dy dx. So when I add that to the other side, I'll have 1 plus 2xy, or 2xy plus 1. And now everything over here has a dy dx, so I can factor out that dy dx and divide by that quantity. So this is what I mean. If you can see where it's going and jump right to that next step, where you factored it out and divided by this quantity, I'm totally fine with that. Just don't try to do too many things at once, so you make silly, sloppy mistakes. That's the number one problem here, is bad algebra in calculus. That's what the AP graders say year after year. Okay, so dy dx will be 1 plus 2xy divided by this big quantity of 6y squared e to the 2y cubed minus x squared. And there we go. There is our derivative dy dx for that problem. Okay, so hopefully you saw enough to get the hang of it, and threw some chain rule and product rule in there. So if you have any questions, feel free to email. Good luck and keep working hard.